My name is Benjamin Phillip, and like Brian just said, I'm a 17-year-old high school student based out of Bangalore, India. I'm the maintainer of Erlang's Apache Arrow implementation and also a frequent contributor to the NX project and HexPM. You can find me on email, GitHub, and Twitter, the links below. So over the past few years, we've seen AI and ML gain more and more relevance in various industries. It's used in scenarios such as all the way from personalization to autonomous vehicles, fraud detection, and even environmental monitoring. It's actually a decades-old idea, but it has come into recent light due to significant improvements in computing power. The term AI and ML can refer to everything from large language models like ChatGPT to simple neural networks like MNIST and even linear regression. And to drive home the fact that AI is a very real thing nowadays, that first point was generated by ChatGPT. So you'd want to use ML from within Elixir. And the first library that you would reach out to in order to do that is Bumblebee. Bumblebee provides ready-to-use pre-trained models, which you can start using with 2 or 4 lines of code. It pulls the model and the trained data from Hugging Space, which can be thought of as GitHub for AI. If you want to know more about Bumblebee, I recommend checking out this talk by Jonathan, which he gave last year here at ElixirConf EU. He's the maintainer of Bumblebee, by the way. So ultimately, Bumblebee is a layer over Axon. And Axon provides a way to represent neural networks for Elixir. It also provides an API for model creation and training these models. And if you want to know more about Axon, you can watch this talk by Sean, Axon's maintainer. But ultimately, all neural networks are just tensor mathematics. And the tensor mathematics within Elixir are powered by numerical Elixir, which is a tensors library for Elixir, which provides tensor maths as well as primitives for linear algebra and calculus. To know more about numerical Elixir, you can watch José's talk from Lambda Days 2021. But the important things and points from José's talk that I'd like to highlight is that Erlang is slow, and implementing the tensor maths for this in native Erlang is not feasible. So the computations are powered by third-party backends like Google's XLA, Facebook's libtorch, and Hugging Face's Candle. NX additionally provides a DSL to define numerical definitions, and JIT and OR ahead of time compile these into functions for the CPU and GPU. And the ultimate goal of enabling and providing you tensors within Elixir is to use the Erlang VM's capabilities and apply them to the space of machine learning. And what this implies is that models can be run concurrently, partitioned across several GPUs, distributed over multiple nodes. And this is quite a big feat. And Sean Moriarty gave another talk last year about how these abilities which NX Pro has simplifies traditional ML ops significantly. But today, I want to discuss the nitty-gritty of how exactly NX achieves these goals, and additionally discuss the pitfalls to keep in mind in its approach. Finally, we'll talk about the performance tuning and performance characteristics of NX itself. Now, the simplest solution to this problem of running models is to just infer your models on the fly within your Phoenix controller or your live view instance within a simple task. Now, the problem with this is that the performance of this approach tends to be rather unpredictable. And depending on the load, it can be very unreliable. To illustrate this, we can benchmark it. In my benchmark, I benchmarked ResNet against random images from the CFAR10 dataset against 1, 10, 100, and 200 parallel requests within Benchy. In addition to that, I also benchmarked a vanilla inference style, which is manual inference with Axon, and the regular inference style via nx.serving run, just to eliminate any doubts of overhead by Bumblebee. I could have additionally, ahead of time, compiled the Axon model, but I didn't do this just for the sake of conciseness. So these are the benchmark results I got. And to put it into words, the regular method has similar performance to vanilla, and it's just barely slow, very slightly slower. The latency grows somewhat linearly, and the reason I say somewhat is that CPU cores tend to have a boost when they are not completely used up. And if you have a computation which is less memory intensive and more computationally intensive, once you have cores filling up, you will notice significant decreases in performance. And the most important thing that I'd like to highlight is that post 200 parallel requests, my Beam instance was killed by the Linux kernel. So the main problems with this approach is that the latency is inconsistent. If you've got a single request, it will take hardly a few milliseconds. But once you get 100 requests or more, each inference can take up to 30 seconds. Very significantly, it can bring out the entire Erlang VM as you may run out of memory and you'll be killed by the kernel. Generally, this approach assumes that you have an infinite availability in resources. And this is not a feasible approach, as AI models, though feasible, are still extremely resource intensive. And the solution to this problem is to just batch your computations. We know that the system can handle certain loads, and we know the performance characteristics of certain number of parallel requests. So the simplest thing is to sort our requests into manageable amounts. This is an age-old solution to various data processing tasks. And the main benefit of this solution is that you get consistent latency and throughput. But the first problem that we've got to solve by batching is how exactly does applying the computation on a batch work. So internally within nx.serving, inputs are batched together using the nx.batch module. And this internally corresponds to the input tensors being stacked or concatenated. The computation is applied on the entire batch at once, or in this case, the entire tensor at once. And what you get is a result tensor with the results for each of the requests stacked into a single tensor. And the end result of this approach is that n calls to the GPU is replaced by a single call. And this has significant performance benefits. So now that we've got a way to apply a computation on a batch, we want some way to accumulate requests and batch them. So the requirements of such a system would be able to batch inputs to a maximum size in as define how big the batch gets. And secondly, we want to define how long the batch should wait in order to get filled. The way NX serving solves this is by managing requests by a gen server, which batches each individual requests into a batch. Subsequent batches are then enqueued and executed sequentially. The batches themselves are executed with a task, which is supervised by a task supervisor linked to the gen server itself. The batches are timed out using a simple process for send after message. So now that we've got basic batching working, we can start encapsulating some extra functionality to this. For example, any computation will have some pre and post processing that needs to occur. For example, an image binary may need to be converted to a compatible tensor, and the model inference output from a model will have to be converted to a human readable label. And this is, and such computations are common for all requests, just like the model itself. So it makes sense to just associate the processing with the batching. So the way this works is that you pass pre and post processing functions to the batching API. The pre-processing function needs to return a tuple with the NX batch along with the info, any client info from the input. The default for the pre-processing function is just a tuple with the identity function. The post-processing function has a similar input, except that instead of a batch, we've got a tensor, and it defaults to just returning the tensor itself. And the way this works is that pre and post-processing functions are run within the caller process and not in any separate task, hence the client prefix. So we also additionally want to be able to use all the resources within a single node, in as all the GPUs in the CPU. The various devices or partitions that you can use are determined by your definite compiler or your backend. Your computation or model is jittered for each partition, and the partition for each request is decided on batching. And the benefit that this gives us is that we are now able to run device number of batches at once. So if you've got 2 GPUs and a CPU, you're able to run 3 batches parallelly. One important thing to keep in mind is that device transfers are not yet handled by NX serving. So what this means is that there may be edge cases where tensors allocated in the CPU will be batched on the GPU queue. And what this will result in are certain errors. And typically you can just ignore these. But if this becomes a real issue, you can transfer your tensor to the binary backend on pre-processing. So now that we've got a fully working solution for a single node, we want to distribute it along many nodes. And the way we do this is that we maintain a cluster of servings with the process group module. When a request comes, we first check if there is a node, a serving present locally in the node. And if it is not present, we select one randomly from the cluster. Each serving is duplicated in the cluster partition number of times. And what this means is that nodes with more partition will tend to get more load. But an important thing to keep in mind when you're distributing like this is that tensors need to be transferred from one node to the other. And this is handled by the distributed pre- and post-processing callbacks. And they default to the identity function, but you can use this to copy the tensor to the binary backend. Additionally, NX.serving also supports streaming inputs and streaming an output. I'm not going to be talking about how this works, but in order to use it, the client pre-processing function needs to stream a nx.batch. If your numerical definition has any side effects like IO, the side effect will need to be handled by the client post-processing function. Unfilled batches with side effects will be padded, and this may have performance hits. For more information, you can look into the NX serving docs. So the last scenario that we need to handle is serving multiple models. It's it's a very common scenario that you've got multiple models running in an application. For example, image classification or text generation, and initiating multiple servings for this can result in race conditions. So the way to support this is that we introduce something called a batch key, and as a key associated with a batch. So you may have a ResNet batch key, and you may have a stable diffusion batch key. And your client, the various processing functions will pattern match on the batch key and apply the requisite computation. So now we've got a working solution. And we're at the point where we need to understand how we can tune NX.serving to get the most performance. There are two parameters which NX.serving provides for us, and one is batch size. And increasing batch size leads to a higher throughput, but increased latency at once as well. Increasing it also increases the amount of memory required at once, and batch size should be slightly larger than most common batches in order to reduce the number of GPU calls. The other parameter is batch timeout, and this is again useful for reducing the number of batches, but it can result in an increase in deviation and latency. So one approach you could take to find a good configuration if you've got only a CPU is set the batch size to a very high value. Then you can experiment with batch timeouts between 0 to 10 milliseconds. And what this does is it ensures a consistent iteration rate. Individual calls to the CPU are not expensive, and we want to prevent the CPU from idling and accumulating larger batches. If you've got a GPU, this is what you could do. You can set batch timeout to a high value, and then tune the batch size to achieve a desired balance between the throughput and latency. And finally, we can tune timeout again to control the tail latency when you have lapses in load so that the batch doesn't block. And what we're doing by this is that we minimize the number of GPU calls. Individual calls to the GPU are more expensive than calls to the CPU as the GPU is further away. But conversely, to CPUs, having larger batches are not a big hit in performance and latency. But ultimately, the best way to configure is to just test your configurations. You can gain more insights about your production environment using the telemetric data generated by NX.serving. And one thing that I would like to add, that apart from this, a solution might be to just add more nodes. When I was researching for this talk, I benchmarked NX.serving with some, and once I got to more than 5,000 processes, my Beam instance used to be killed despite batching. And the reason for this is that the act of just batching 5,000 images takes up a lot of memory. So in case you run out of physical memory like that, the solution may just to add more nodes. Now, some further ideas and that I've had. So it is technically possible to fill all the batches of all nodes and accumulating more and more batches. And conversely, it may be possible that a lot of nodes are idle at the moment. So we want to reduce the amount of GPU time for cost reasons. And it would be, it'll be pretty cool if you could scale up and scale down the number of nodes according to your load. So this can be easily implemented with Flame. And Flame is a new pattern introduced by Chris McCord, and he's going to be giving a keynote about it at the end of the conference if you want to know more. Another feature that could be added is multinodal tensor transfers. So right now, if you want to transfer your tensor between nodes, you have to transfer the node to the binary backend as an intermediate step. And this is inefficient because what you're effectively doing is transferring to a Erlang native format. Other stacks offer solutions to transfer your tensor between GPUs, between nodes in a much more efficient manner with libraries like NVIDIA's NCCL. And it might be worth adding support for this. So to conclude, computations on the fly are very unreliable, and it may even potentially crash your Beam instance. NX.serving enables you to batch multiple computations into a single computation. And these batches can be partitioned across GPUs and distribute across nodes. And finally, I recommend that you tune by load testing your configurations using a tool like JMeter or SUM. Questions?
All right, so if anybody has any questions, you can post in the Hoof chat in the Q&A tab. We'll give people a minute to see. How long have you been working with NX and doing the contributions you've been doing?
I think the past 2 or 3 years. I started working on it in about 3 years ago, 2021.
Nice. Did you, yeah, never mind. Cool. And still have a couple minutes in case anybody has any questions. And of course, if anybody still has questions, then Benjamin can check in later after the talk and answer them directly in Hoover. But okay. Oh, yeah, there's a question from Mark. Have you tested ARM server with NX? I assume that's the CPU ARM.
So I've personally not tested it, but backends like XLA, Google's XLA and PyTorch, to my knowledge, do run on ARM. One of NX's maintainers, Paulo, has managed to get NX work and Livebook working on a Raspberry Pi. So yeah, and to my knowledge, NX does run on ARM.
I mean, I know that a lot of people use NX on the new MacBooks, which are ARM, so that somehow is somewhat compatible.
Yeah.
Yeah. Cool. All right. Yeah. Christo says wishes he was doing stuff like this when he was 16 years old. I think the same. Awesome. Well, thank you so much again, Benjamin. Thank you, everybody.